right. Hey, everybody. My name is Frederick. I'm here together with Venkatesh Prasad, and we will talk to you about the Modeling Toolkit Standard Library that you are able to use to quickly get out to speed with an MTK model. So just a very brief overview of MTK Standard Lib. It's a library. It's in the name. It's of reusable components from multiple different domains. And with domain, I mean things like mechanical, thermal, magnetic, hydraulic, and so on, right? It's composable with the SciML ecosystem that comes from just using Modeling Toolkit, right? And as of very recently, it's also ready for the graphical user interface. So as a library, it has lots of different sub-libraries, as we see some of them there. Basic blocks are things like PID controller, state space system, low-pass filter, gain, matrix gain, and so on. We have mechanical components, so those would be your masses, springs, joints, gearboxes, all of that. Electrical, you can kind of figure out what's in there, but also a few non-trivial libraries like thermal, magnetic, and also not shown on this slide is hydraulic. So thank you, Brad, if you're here, for providing that. And of course, each of these libraries have a lot of components inside of them. And let's see. Yep. When I say a component, we have a screenshot from the graphical user interface here with a kind of the component library part of that. It's things that, like a capacitor, for instance. And what makes it a good component? It's something that has an equation associated with it, and you only have to write that once. And then you can put that capacitor into all of your models and just change the parameter. Maybe you would like to have a more fancy version of a capacitor that also has an internal resistor. Okay, you can make your own fancy capacitor and extend the library that way. So it's very simple to extend. You can extend by implementing new components where you write the equations. If you are the domain expert, you can do that. You can also write components that are composed out of several lower level components. So for instance, if you compose a bunch of capacitors and resistors, you create perhaps a low pass filter. So those are different ways you can extend the library. Another nice feature, of course, it uses Modeling Toolkit, but with that comes a composability with the rest of the SciML organization. So we had a talk a couple of hours ago on the QR code there for doing control analysis using Modeling Toolkit Standard Library models. You can also do things like structural identification. So here structural identifiability kind of analysis. So here we load a package with that particular name, and we call the function assess local identifiability. And the model we pass in this case is an RC circuit. And it turns out that you can not actually identify R and C separately, because the product of R and C is what we call a time constant. You can identify that. So here we say, can I identify the function or the expression R times C? And it responds with 1, which means yes, you can. All right, cool. So you can use interesting things from SciML like that. I said it's ready for the graphical user interface. Here we show a screenshot of that. There was a video shown in the Julia Hub sponsor talk. We see, maybe I should stand here. We see here a number of components, and the way you kind of put these components together is by connecting these lines, all right? And each such line between these colored blocks is represented in code with a connect statement. So if you write this in code, you would have connect the negative pin of the resistor to the positive pin of the capacitor. That would be one connection, and it's visualized here as a line. And then, of course, this is a simple model, but with this you can build incredibly complicated and complex model. For instance, this could be a car where you have suspension and wheel and motor and all of that stuff, right? And the key point is that you don't want to start modeling a car by writing down the equations. You probably want to start using higher level components that someone else have implemented for you. All right, and with that, I would like to hand over to Venkatesh, who will dive into more detail.
Yeah, hi. So in the gray picture is the old way we wrote the ODE systems in the standard library. So we recently switched to using MTK model macro that MTK provides. So this is more convenient, as you can, is more expressive, and also it provides it automatically generates a structure which then we can plug into GUI and get the components based on that right out of the box. So I'll go into detail of how this works. You can have your parameters and variables in the parameters and variables block. You have to line separate them, and you can have their default values. These default values are set. If the user has his own default value, what happens is all these parameters and variables are implicitly promoted as keyword arguments. So user can pass his own default value if he wants to change. And then in this example, it's EMF, so it has voltage and current as well, and a positive and a negative pin. In standard library, there is a component called oneport, which already defines them. So we just want to extend them. So we have an extend macro, with which we are specifying that we want to pull out the V and I, voltage and current variables, and we are naming it as oneport. One thing to note that is the variable list has to be a tuple. So if it's just V that you want to pull out, you still have to make it a tuple. And then it uses the extend function of MTK. It's equivalent to that. And then EMF also has two more components, that is flange and support, which is from rotational library. Here, if you notice, flange has set a default value to phi. So that's how you specify to the MTK model macro that, OK, this flange dot phi can have a value set by user. So user cannot now pass any value to support, but if he wants to set any default value, he can set to the flange dot phi. So for that phi, he can pass the default value. That is a toggle that you can use for passing the default values to the subsystem. And then at equations block has all the equations that are specific to EMF, what makes it EMF module. And if you notice at the end, there is no ODE system. You don't have to define it again. So that is taken care by the macro itself. It sees, OK, these are the parameters, variables, components, and equations. And OK, this is the ODE system I need to build. And one convenient thing it does is now you no longer have to specify all the systems it has. And sometimes we miss out one of those. And we build really large models with those. And we get an imbalanced equation. And it becomes a debugging nightmare. That's no longer the case. And then you can create EMF component. Either if you're using @named macro, it automatically passes the name. And also, you can use a dot. Subcomponents can be accessed via dot. So flange.phi would work. If you are doing it as a normal function, then the notation changes to double underscore. So it would be flange double underscore phi. That's the notation we are following. And you also have to specify the name of that EMF component. And then if you see the next picture, that's the generated structure. So it already knows what components there were and what variables there are, and also the keyword arguments. So K had nothing, no default value, so it is promoted as OK. And then independent variables are also there, and what is extended, parameters and equations. So the advantage of this is now you can just plug this into the GUI, and GUI can define the ports there are and what equations to expect and what values, keyword values the user might provide. So it is very much pluggable. And then I would like to briefly go over how we can stack all these various components that library has into one big model. Here I'm using electrical submodule and rotational submodule and blocks. And then I'm going again with an MTK model macro in that I'm defining components, which are from electrical library, the ground, voltage, resistor, inductor, and EMF. And step function is the waveform that we are expecting the source to have for the voltage source and one more for the torque. So those two are coming from the blocks. And then torque and inertia, damper, all these are from the rotational library. So this continues to the next page. We define how these are connected. If you can see that the flange and the support have internally, they have phi angle and tau torque. And the electrical components, N and P, are the negative and the positive pins. So they have voltage and the current as their variables. So you do connect, negative pins and the positive pins and flanges and the supports so that those variables are connected together. In case you miss and connect a electrical pin which has a different set of variables to a flange, then it just gives you an error saying that, okay, these cannot be connected. So you don't have to worry, and all these connectors has an information that, like components can be connected, and you can see that everything here is in the same block, sort of electrical and rotational part is in the same block again, while not causing any problem. And then you just create a system out of it, and you structurally simplify, create a ODE problem, solve it, and plot the value. It all works. Next thing is, as soon as I run the DC motor, it gives you a structure. So even for this, I just plugged in all the sub components in the library and created a larger model, and it gave you a structure. So this structure can be again used for GUI to have a tile for DC motor itself, so that that just works. And if there is one more set of DC motor, if there are other things, those things can be connected together as well. And no additional work is required. It just works directly. And then this is how the GUI looks. Yeah. 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 So Julia Hub now has a tile for Julia Sim. There you have all these components from standard library, and also HVAC and batteries are also there. So you can use all these to build, drag and drop and build a circuit. And then, yeah, it uses the structure that I showed earlier. And you can also view the code and also get the plots. You can change the timestamp, and variables and all those things can be done. Okay. Yeah. So with this, the future plans, for the DSL, we are also adding if-else conditions, so that currently, if there is an equation saying that, okay, if this particular parameter is false, don't pass these variables, that doesn't work. We will be adding shortly. And subcomponents currently have numerical default values. We want to switch that to symbolic. That is coming as well. And more readable error messages is something we are adding as well. And additional libraries. We want to add noise and discrete blocks, all these libraries. And if you have any libraries of your own, you can add them as well. And the GUI support, we are trying out what works best for various domains. We already have an idea of, okay, if these domains, models are from these domains, then this is how GUI might be more friendly. So if you have your own library, then do add it and try out and give us a feedback on what GUI should look like for your particular library. And if you have any components in mind, then just add to standard library, and directly that will be part of GUI. And special acknowledgements to Brad and Valentin, who contributed some of the submodules of standard library. And yeah, for more on this, for the documentation, you can scan this one. And for standard library, it's the other one. You can try out and create issues, add more models. Yeah.
All right. Any questions? All right, lots of questions. I don't know who was first. Let's start. Yeah. All right. Johnny?
Yeah. So the MTK model macro, can that handle, for example, like if you have certain variables that are actually vectors or something like that, and normally you kind of have to manually scalarize them to create, the different variables. But can that handle vector components like that?
Do you mean the variables or the components?
So, like, let's say, like
Yeah, that isn't supported yet, yeah.
So the limitations there are the same as for Modeling Toolkit, and the answer is that it's gonna require JuliaCon compiler to handle array variables the correct way. Yep. Yeah, Torkel.
So you have a lot of specific packages which feed into Modeling Toolkit, and like this more general. Do you have like a good idea or guideline for like when like a new type of domain feature would fit in the Modeling Toolkit standard library, and when it should more like fit into a separate package?
It should be reasonably reusable for a wide community, right, to fit in the standard library. Having said that, if you are implementing models for organs in the body or something like that, there is a fairly wide community of people who are interested in those. There is no harm in adding such components to the model library, provided that it provides a fairly comprehensive model library. If it's just a very small part, maybe it's not worth it. Also, it should follow a certain standard in the sense that it should be easy to maintain for the maintainers of the model library, unless you are willing to volunteer for a very long time there, of course. Yep. Yeah, please volunteer. But the structure of it's very easily extendable, and it doesn't have to necessarily live in the standard library. It can live in its own package as well. The standard library is as first class as anything else, really. The only thing that is required is that you implement your model using this MTK model macro so that the structure is automatically there. So in that sense, the standard library can serve as a reference implementation for how you implement those. And if you follow the best practices we try to establish there, the library you provide can live absolutely anywhere, really. Yep.
Yeah, I think the last thing is important to emphasize, right? So the Modeling Toolkit Standard Library lives as a reference library for what Modeling Toolkit component library should look like, right? So if you ever want to know, like, oh, I want to build my own weird library, you can always look at the Modeling Toolkit Standard Library as an example, and anything that follows that form is something that's compatible with all sorts of different things, all the downstream Modeling Toolkit stuff, but also the GUIs that are being built and all the things that are like the surrogates and everything. All of this is all compatible with whatever follows that, right? Now, whether something can be in the Modeling Toolkit Standard Library or in a separate repo, that's more organizational stuff at that point. Modeling Toolkit Standard Library right now is kind of targeted towards things like you see in the ModelingToolkit Standard Library, though it's not necessarily restricted to that space, right? We just haven't done things beyond that. But we are interested in if someone like says, oh, I have this kind of, drive JSON string or something, and, if you want to do it. I think that the key thing about it being in ModelingToolkit Standard Library rather than a separate repo is that things in SciML have a nice support structure, right? So with SciML, we tend to have, the Julia Lab and all sorts of people, and, all these contributors that'll help keep things alive, right? And so, it's like, is this for your own project? Do you want to just play around with it? Or is this something that you think is really reusable and you want to make sure it's kept alive, but you also don't want to maintain it yourself, right? That's kind of a place for ModelingToolkit Standard Library.
There is one, yeah.
Talking about Modelica and other modeling frameworks, one thing that always comes up in discussions with my collaborators who are clinicians is units. So my units are SI units, and Modeling Toolkit, by the way, almost like has design units, but many of the models are in physiological units, millimeters HD for pressures, etc. Is there a scope for including unit book in that whole thing, in that acausal modeling framework, that I can define something with units defined in the components that are then transparently translated to whatever unit comes in?
Units are already allowed in ModelingToolkit. There's a separate documentation page that describes defining units and things. And it will automatically do unit checks
Yeah.
and unit validations.
Only the checks and validations.
So here, with the description, you can also add the units while defining the parameters and variables.
That's
Yeah.
the unit that it expects the parameters.
Yeah, yeah,
So that's
yeah.
basically like docstring. What I'm thinking about is a bit more so I can connect, for example, something that comes in with a pressure in pascals, but that big component expects the pressure or gives outputs of pressure in millimeters internally. And
Okay.
is that translatable? In other applications, when I hand code my ODEs, unit works and it all translates through, but in the acausal
So So this has different submodules and everything. If you see, it has single release for all those things. So if you add some components to one of those libraries, it's still entire standard library is released. But yeah, it is structured into sub modules, and those submodules have a few more modules, and it's like that. Yeah. Yes. Yes.
It's a fairly lightweight package. It is essentially
That is
just
true.
symbolic models in there.
That's true. It's just this much.
Yeah, certainly. So
Okay, I need to log in.
the reusability, we are supported by the Julia package manager. So a model has all of the support of a traditional Julia package, right? In terms of reproducibility, that you can instantiate exactly the same thing at a later point as you are using right now.
So
And
this type.
For launching the graphical user
Yeah.
interface. Yeah. So you can access the graphical user interface from the Julia Hub website. You need to log in, create a free account, it's free, and then there is an app under applications that is called Julia Sim. And if you launch that, you should get launched into the graphical user interface. But to continue more on the traceability, a model in the graphical user interface is just a text file, and it's fairly readable, human readable. So that is managed by Git. Well,
So the thing is, you can drag and drop and build your own model, and you can export that. And you know, if there is a model already, that can be re-imported, and you can even save, and you can you know, make that one of the other tiles. So sort of, if there was blocks, the DC motor at the end had its own structure, right? So that could be its own tile at the end. So yeah, that can be again connected with something else.
so in theory, when you have saved a model to text, and if you would edit that, we can obviously load a model from disk also. But I don't expect the syntax of that file to be something you would necessarily like to edit. You can obviously do things like change parameters and all these things. That's fairly straightforward.
Yeah.
But there is some layout code in a language that is essentially not Julia, right? So it's not as nice, at least, to edit that way. All right, since we have 4 minutes more, I would like to mention one additional thing if you create your own libraries. The Modeling Toolkit Standard Library contains one submodule called blocks. And the block, what makes something a block is that it has an inherent causality. So Modeling Toolkit is an acausal language. A resistor doesn't have an input or an output, it just has 2 pins. But the block modules actually do have causality. So they are things like a source. Here is a sinusoidal signal. That only has an output. It's things like an integrator. It integrates the input to provide an integrated output. If you are relying on things, building models that take inputs, try to make use of the components that are called real input and real output, and they're also eventually Boolean and integer inputs and so on, because that would make it fit together with a lot of other tools that rely on this kind of input and output functionality. So that's one thing you could potentially keep in mind. All right, cool. Thanks.
Thank you.